Good day. In this video, you're going to learn about electric potential. Electric potential energy. It is the same effect for electric force. Okay? Your energy is present based on the position, but your position is independent. So there is a change in position. Hence, could be it could affect your change in energy. Okay? It could change your energy or the amount of potential energy. Remember, unless otherwise stated, test charge is positive. Okay? UE stands for your electric potential energy. It is equal to your FT. Since we are talking about electricity here, your F here is the electrostatic force. Multiply it with the distance D or the distance between two charges. Remember that your F here is defined as your column constant. Okay? Multiply it with the amount of the product of the charges Q1 and Q2 all over the distance between the charges. Okay? And then we're going to substitute here to your equation UE is equal to FD. So this gives us the following configuration as your columns constant, multiply it with the product of your charges all over the distance between the two charges, multiply it with the distance between the two of the charges. But the other one is squared, so this cancels out, okay, your R and then the 2 here. So further simplifying your electric potential energy to columns constant, multiply it with your product of two charges in column squared all over the distance between your charges. The electric potential difference. Okay? Electric potential is hard to understand but easy to measure. It is the potential energy per unit charge. It is related to electric potential energy and the electric field, commonly called as voltage. Okay? Just remember this. 1 volt is equal to 1 joule per coulomb. So this is in SI unit as well. So if we're going to define electric potential, the electric potential at a given point is electric potential energy of a small test charge divided by the charge itself. So we are given with the following, your volts or voltage here would be equal to potential energy all over the charge. As you can see here, 1 volt is equal to 1 joule per coulomb for SI units. Okay? If we're going to further expand the formula, and we are given with 2 points or 2 charges here, or 2 points, okay? Your delta V or voltage B's and A, okay, could be expressed as a change, okay, would be equal to the change of your electric potential energy all over the charges. Okay? This is equal to your work of charges A, B per your given charge. Okay, so delta V now would be equal to delta U all over your charge, or is equal to the negative work of your charges AB all over the charge. Say for example, we have two charges here as AB. Okay, the work potential energy and electric potential, the work done by the electric force as the test charge, positive 2 times 10 raised to negative 6 coulomb, moves from A to B is 5 times 10 raised to negative 5 joules. Okay? Find the difference in EPE between these points. Okay? Determine the potential difference between these points. For letter A now, if we're going to solve for your work, okay, the difference between the electric potential energies of your A and B, UA minus UB gives us your negative WAB. Since we are given with the work from A to B as positive 5 times 10 raised to negative 5, and we are pertaining it to the work A to B. So let's get the negative, okay, of the charges. So this is negative WAB. Okay. This is equal to negative 5 times 10 raised to negative 5 joules. And then for letter B, determine the potential difference between these points. Okay? Delta V would be equal to your UB all over QO minus UA all over your QO, or it is equal to negative work AB all over your QO. Substituting the values, delta V is equal to negative 5 times 10 raised to negative 5 joules per 2 times 10 raised to negative 6 coulomb. This is equal to negative 25 volts. Okay? The accelerations of positive and negative charges. A positive test charge is released from A and accelerates towards B. Upon reaching B, the test charge continues to accelerate toward C, assuming that only motion along the line is possible. What will a negative test charge do when released from rest at B? So this is illustrated here as the movement of the charge from C to A. Okay? There are distances for A to B and B to C. So negative charge will accelerate towards your A, okay? Since it has higher potential. A positive charge accelerates from region of higher electric potential toward a region of lower electric potential. A negative charge accelerates from a region of lower potential toward a region of higher potential. We now include electric potential energy as part of the total energy that an object can have. Your E now is equal to the half of mv squared plus half of IW squared plus your potential energy mgh plus half of your constant x squared or displacement plus your electro-potential energy. 1 electron volt is the magnitude of the amount by which the potential energy of an electron charge changes when the electron moves through a potential difference of 1 volt. So 1 electric volt is equal to 1.6 times 10 raised to negative 19 volts. Say for this example, the conservation of energy. A particle has a mass of 1.8 times 10 raised to negative 5 kilogram and a charge of 3 times 10 raised to negative 5 coulomb. It is released from point A and accelerates horizontally until it reaches point B. The only force acting on the particle is electric force, and the electric potential at A is 25 volts greater than at B. What is the speed of the particle at point B? If the same particle had negative charge and were released from point B, what would be its speed at A? Remember, if we're going to proceed with the solution, we are given with the diagram here as your positive charge moving towards your B, okay, with a velocity of VB. Your velocity for your A instantaneously is equal to 0 meters per second, okay? This is for your letter A. For letter A now, if we're going to further simplify the formula, 1 half mvb squared plus ub is equal to 1 half mv squared A plus ua. 1 half mvb squared is equal to ua minus ub, but your U is equal to your charge, multiply it with the amount of voltage. Okay, if we're going to substitute this one, this becomes 1 half mvb squared is equal to QO. Multiply it with your change of voltage of charge A and B, VA minus VB. To simplify this one, this gives us with the formula VB is equal to the square root of twice of your QO or your charge. Multiply it with your VA minus VB, okay, all over M. If we're going to substitute it now, twice of your charge as 3.0 times 10 raised to negative 5 coulombs. Multiply it with the changes of the voltages, okay, as 25 volts. Multiply or divide it with the mass of the charge at 1.8 times 10 raised to negative 5 kilograms. This gives us the velocity at VB is equal to 9.1 meters per second. Please do not be confused with the small letter V with bigger B. Your bigger V now here pertains to your voltage. Okay? Your smaller v here pertains to the velocity. For this type of problems, you may memorize this formula as VB is equal to the square root of 2QO, multiply it with the change in your charges as VA minus VB all over M. Okay. For part B, if we're going to consider your A now moving, okay, your B as stationary or VB is equal to 0 meters per second, they will have the same speed as in letter A, but it is in the opposite direction. So difference in potential. What is the potential difference as a particle moves in an electric field due to the electric force as point charge moves from A to B? Since the force is a function of distance, must use calculus. As you can see on your diagram, we have your charge B, okay, with lower downhill potential, okay, or lower potential energy, but as it moves to your point A, it has higher potential energy. Your charge now here, okay, we have the with respect to the points A, okay, we're going to name this as the distance RA, and then the distance between your charge here to point B as your distance BRB. Okay, the movement of your positive charge here, okay, since this is towards your right, this is positive F. Okay, so if we're going to integrate now your calculus here, work now is equal to, okay, the integral of your column constant, multiply it with the products of your charges Q and QO all over your distance squared and differential of your distance with your lower limit as RA and your upper limit as RB. Further simplifying the formula, since your Q and QO and your K here or your columns constant are constants, okay, we're just going to bring it out, which leaves us with the following expression as the integral of your differential of the distance all over distance squared. The distance here are the distance between the charges, okay, or the charge that has moved, with your upper limit as RB and lower limit as your RA. Okay? If further simplifying the formula, we're going to apply this one, your power formula. Dx all over x squared is equal to negative 1 all over x. Okay. If we're going to apply this one on the formula of your work for your electric charges, okay, further simplifying this gives us the following. Okay. Delta U now is equal to negative W. Delta V is equal to delta U all over QO. Hence, your change in voltage is equal to negative work at points A, B all over the amount of charge. Okay. This is equal to your columns constant, multiply it with the charge all over the initial distance, okay, minus the charge or columns constant, multiply it with the charge all over the final distance which it has moved from point A to B. Okay. Total potential of all points charges. Your V now is equal to this one. Kindly memorize this one or know this one as the your voltage is equal to your columns constant. Multiply it with the summation of individual charge all over the respective distances with your I as your limit and your upper limit as depending on the number of charges. Okay. We have your fifth example, the potential of a point charge using a zero reference potential at infinity. Determine the amount by which a point charge of 4 times 10 raised to negative 8 coulomb alters the electric potential at a spot 1.2 meters away when the charge is A positive and B negative. For letter A, so since this is the amount of charge for 8.0 times 10 raised to negative 8 column. Okay. V now is equal to your column's constant known as 8.99 times 10 raised to 9 Newton meter squared per column squared. Multiply it with the charge Q as 4 times 10 raised to negative 8 columns. So since this is in letter A, so we're going to assume the charge as positive all over 1.2 meters. Okay, this is the distance between the two charges. Remember that the arrow represents the movement of lower potential to higher potential, as you can see here. Okay, we are given with this distance at this point at the higher potential as 1.2 meters. Okay, if we're going to further simplify the values we had just plugged in for letter A, this gives us your volts as positive 300. Okay, since this is in higher potential. Okay, for letter B, since we're just going to change the sign of your charge here as negative, okay, your voltage or the amount of voltage is in negative as well. So this gives us negative 300 volts. Okay, so this is on um, lower downward of your energy or lower point of your potential energy for electrostatic forces. Okay, for letter or for sixth example, the total electric potential at locations A and B, find the total electric potential. Okay, we are given with this following diagram. Okay, your charge here, A times 10 raised to negative 9 columns here, has a distance between point A to the charge itself as 0.20 meters, and then the distance between point A to B as 0.20 meters, and then for the distance between this charge, this letter or point B to this given charge as negative 8.0 times 10 raised to negative 9 columns has a distance of 0.40 meters. How are we going to solve now for the charges, okay, A and B? To solve now for the charges A and B, remember that we're going to use this formula. V is equal to your columns constant times the summation of individual charges all over their respective distances. Since we are talking about point A here, okay, your VA would be equal to the column constant K, 8.99 times 10 raised to 9 Newton meter squared per column squared. Multiply it with positive. Okay, since this is a positive charge, so positive 8 times 10 raised to negative 8 columns. Okay, all over 0.20 meters. Okay, plus, okay, we have this one going to point A. Okay, so negative 8.0 times 10 raised to negative 8 columns. Okay, multiply it with the columns constant at 8.99 times 10 raised to 9 all over the total distance here. So 0.20 plus 0.40 meters. So this gives us 0.6 meters for here. This is equal to positive 240 volts. Okay, that is the voltage at point A for both charges. And then for the voltage at point B, okay, VB would be equal to 8.99 times 10 raised to 9 newtons per meter squared, column squared, multiply it with the charge at A. This is 8.0 times 10 raised to negative 8. This is correct, incorrection, negative 8 columns per 0.40 meters. Okay, this is calculated as 0.20 plus 0.20. Okay, plus 8.99 times 10 raised to 9 Newton per m squared per column squared. This is your column constant. Multiply it with the amount of charge in this one as negative 8 times 10 raised to negative 8 columns per 0.40 meters. Okay, this one, the distance between this charge and point B as 0.40 meters. So this gives us a value of 0 volts. Okay, so we have your equipotential surfaces. An equipotential surface is a surface on which the electric potential is the same everywhere. V is equal to KQ all over R. The net electric force does no work on charge as it moves on an equipotential surface. This is because electric potential for the whole is equal. The electric field created by any charge or group of charges is everywhere perpendicular to the associated equipotential surfaces and points in the direction of decreasing potential. So we have this following diagram, okay, which represents the movement of your positive charge towards your negative charge. Okay, so we have your electric potential in parallel plate capacitors as electric potential average would be equal to your negative voltage all over the distance between the plates. Okay. The electric field and potential are related. The plates of the capacitor are separated by a distance of 0.032 meters, and the potential difference between them is VB minus VA would be equal to negative 64 volts. Between the two equipotential surfaces shown in color, there is a potential difference of negative 3.0 volts. Find the spacing between the two colored surfaces. To solve now, we are given with the voltage as negative 64 volts, okay? And then distance AB as given at 0.032 meters, okay? If we're going to determine now the equipotential of the surfaces or plates, this gives us 2 times 10 raised to 3 volts per meter. Now, find the spacing between the two colored spaces. If we're going to find the space between these two, okay, lighter blue surfaces, we're going to solve it through this one. Since the potential difference between the two surfaces or the two colored surfaces is equal to negative 3.0 volts, okay, we're going to use that value to substitute it here as D is equal to negative V all over E, negative of 3.0 volts all over the one we had solved earlier for the equipotential of the surfaces, okay? E is equal to 2 times 10 raised to 3 volts per meters all over 2.0 times 10 raised to 3 volts per meter. Here, we're going to substitute that here. So this gives us an answer of 1.5 times 10 raised to negative 3 meters. Okay, we have your capacitors. A capacitor is a device that can store potential energy. Usually, they are built by placing two conductors near each other without touching. Okay, for AB, we will only look at the area separating the two plates. We can make capacitors with other insulators separating the two conductors. Okay, we have your capacitors in dielectrics. A parallel plate capacitor consists of two metal plates, one carrying charge positive Q and the other carrying charge negative Q. It is common to fill the region between the plates with an electrically insulating substance called as dielectric. Okay. So we have the following. The relationship between charge and potential difference for a capacitor as Q is equal to CV, or your Q now is directly proportional to your voltage with C as your capacitance. This is used as your proportionality constant. So C now would be equal to Q all over V, or deriving from this formula, getting your C now, or your capacitance would be equal to Q all over V. Okay. This is in coulomb per volt or farad. One capacitance is equal to 1 farad. So this ends my presentation. For further questions, you may message me through our messenger or Facebook Messenger app or through our LMS inbox. Have a nice day.